So problem 2 from the 2017 midterm is about interpolation. So we are given the formula for the second form of the barycentric interpolation formula. So we can see that in equation 4. So we're given some code here and we're asked to fill out some code. For convenience, I have already typed out all of this apart from the header. For your midterm, please type the header. And we want to fill in the missing parts, primarily the part where we are summing the numerator and the denominator separately. So we want to do this summation for the numerator and the summation here for the denominator. So I'll also be going through all of this code just to clarify what is going on. If you already know what is going on, you can please skip and get to the part where I start filling in the code here. So let's go ahead and do that. So as I mentioned, I have already typed out most of the code here. So here we have a function. So just letting you know, whatever your function name is, the file name has to match. If you have your file name and your function name different, or they're not the same, MATLAB will not recognize your function. So make sure that your function name and your file name is the same. Also, here are our parameters. So whatever you input as tau, rho, and x are used in this calculation here. So please do not add or define tau, rho, or x within this function. That's not what a function is supposed to do. It is supposed to input or accept what your parameters are. So in this case, tau, rho, and x, and use those in your calculations within your function. In addition to that, we have p here, which is our output. So whatever we assign to p in our function will then get outputted. So make sure that you define p within your function if you're using p as your output name. Alright, so there are some comments that are pretty straightforward. So here we're getting the number of interpolation points and we're labeling that n. And we are computing the barycentric weights, which we have done in a lab before. So we're saying beta is equal to 1s, n comma 1, which creates a vector of 1s with n number of rows and 1 column. So it's a column vector. And here we're doing a double for loop in which we are carrying out the calculation of our weights, which is not defined in the midterm, but since you don't need to code it, I guess they didn't give it to you. So here, if you just look back at your notes, this should look quite familiar. So now we want to compute the numerator and the denominator, and we assign all of these as zeros. So as I mentioned previously in labs, the reason why for betas we want to assign them as 1s, whereas for the numerator and the denominator we want to assign as zeros, is because in beta we're multiplying, as you can see here. So whenever we're multiplying something to 1, it gives back our original value. And that is why we use 1. If we use 0, if we multiply something to 0, that will give us back 0. And that is not something that we want. On the other hand, if we're adding, like what we have in our barycentric interpolation formula here, if we're adding something to 0, it gives us back our number. Whereas if we're adding something to 1, well, it increases by 1. And that is also not what we want. So make sure anytime you see a product, you are using 1s as your initialization. If you're summing, you're using zeros. And then here we would go through a for loop to fill out the summation, and then after we have our numerator and our denominator, we're going to divide by elements. So we can go ahead and delete that. So let's just focus on the numerator for now and look at what is going on in the numerator. So here we have the summation of beta k times rho k over x minus tau. So in this case, only the beta, rhos, and taus are changing, the x are always constant. So that's why the numerator has to be of size x, because we are always going to result or output a vector, because these are all numbers, whereas this is a vector. So here, if I remember right, we should have numer plus beta k times rho k dot divide x minus tau of k. So the reason why we need a dot operator here is like my explanation from problem 1, whereas these two, beta and rho, are values because we are extracting an element of index k from our vector of betas and rhos and taus. So these two are values, and we're dividing by vector minus a value. So whenever you subtract a value from a vector, it still results in a vector, because MATLAB knows that we're subtracting this value for every single element within x. So since this is still a vector, the denominator, we need to put a dot operator here to tell MATLAB that we're dividing a number by a vector. So that is our numerator, so we can move on to our denominator, which is beta over x minus tau k. So this is very similar to the numerator. Typing this in, denom is equal, we have to spell it correctly, denom plus beta k, remember dot divide x minus tau k. So with that, it looks as though we are done our function. So we can move on to part, I'm not sure whether it's part A or B. Here it is. So for part A, it tells us the cardinal sine function is defined as sine x over x. This is actually a typo. Sine or sinc is actually defined as sine pi times x over pi times x, if I remember correctly. Yes. So we will do the correct, quote unquote, correct sinc function. So we're asked to evaluate the cardinal sine function from negative pi to pi. So let's go ahead and open a new script, and we can label this problem 2. And we can save it as problem 2. And alright, so part 1, we want to plot the sinc function. So we first need to define what x is. So since the question has told us that it has to be from negative pi to pi, we can use linspace from negative pi, pi, and pick a large number. Let's go with 2018 since that's a year. And let's go ahead and plot x and then sinc x. So here, these are the x values that we're plotting, and here are the y values. So since we are evaluating sinc at these x, we don't need to create a new variable. If you'd like, you can, but this condenses things a little bit. So your x and y values. So we can save that and let's go ahead and run it. And we can see that we get this sort of pattern or function here. Of course, in the midterm, you'll need labels, a title, and all of that. But in the interest of time, I'm not going to add them. It's up to you. So we have done part 1. Now for part B, did I say part 1? Part A. So for part B, we want to use our Berry eval function with 21 equally spaced nodes from negative pi to pi. Alright, so let's go ahead and do that then. So here, what we need are our taus. So they have said that we wanted 21 equally spaced nodes. So you don't actually need to memorize what the formula was given from one of the labs. Instead, you can say lens space from negative pi to pi with 21. So what this gives us is equally spaced nodes from negative pi to pi, and there are 21 of them. And rho is just simply sync tau, actually, not sync x. Sorry, I was looking up here, wasn't paying attention. So we have our taus and our rhos, and we also need our x. We can actually reuse our x from the previous one, which is great, so we don't need to redefine what x is. So now we can say y is equal to Berry eval to tau, rho, and x. And let's see what else they want. And that's all for now. So we can go ahead and run this. Let's just plot to see whether we get something, and we get something similar to what we had earlier. So just a note, if you have two plot here, the second one will just overwrite the first one if you don't put figure. So I can tell you that this is actually the second plot and not the first one, because it overwrites. So for example, if I put figure here, then it'll give us two figures and it's quite similar. So there's that. Alright, this isn't actually needed. We're just checking that we don't get any errors. So let's move on to part C. So I don't know why I said part 1 and 2, but let's just go ahead and change that. So what does part C asks? So what is the degree of the polynomial? So that is just a theoretical question. The degree of the polynomial is always n minus 1, so the number of points minus 1. So the degree is n minus 1. So it's equal to 21 minus 1, meaning that is a 20-degree polynomial. Alright, so now we can do part D, which I think is plotting. So let's make a plot containing the following: the cardinal sine function, the 21 equally spaced nodes, and the interpolating polynomial. Alright, so let's go ahead and do figure. So then we get a nice second plot. So we'll have plot x sync x, so that's our first one. And then we want our interpolating points, so we can say tau and rho, and let's just go ahead and put circles. And now we want our x and y. And since this here would probably be covering the exact function, let's go ahead and have it stylize it as dashed lines. So then at least we can see both of them together. Obviously, I'm not going to add legends, title, and axes titles, but you'll need it on the midterm. So we can see here figure 2 that we have everything here, and we can see that both of the functions here. So it's yellow and blue together. So if your functions go missing, just make sure that you have a dashed line so you can show that they're overlapping each other. And we have figure 1 here. Okay, what is part E? So part E is asking us to make a forward error plot. So remember, whatever your numerical result is minus the exact result is called the forward error. So let's go ahead and do that. So part E, let's make another figure. So we'll have x and then absolute value of our sync x minus y. So what this is doing is, as we know, we have our x values, and we're just simply putting our error in here. So we have our sync function with the x that we have previously defined in line 4, and we are subtracting whatever we have gotten, which I have defined as y, in line 10. And since we're taking the absolute value of it, we're just typing in ABS and then put everything in brackets. So let's go ahead and run that again. And we can see for figure 3, we get some interesting spikes here. So this kind of leads up to the next question on Runge phenomena. So let's go ahead and take a look at that. Well, before that, they asked what the maximum error is. So we can easily calculate that by asking what the max of ABS sync x minus y is. So you can see that ABS sync x minus y is exactly the same as what we have plotted. We're just adding the maximum value to it. So now what we should have is just the one value from that vector. I do not want to recalculate all of this, so I'm just double % signing it and running this section, and we can see that the maximum value is 3.013 times 10 to the minus 5. So if we go ahead and plot the error yet again and see whether that makes any sense, we can see that the largest point here is around 3 times 10 to the minus 5-ish, which checks out. So that looks good. Alright, so for the next question, for part G, is Runge phenomena present in this problem? How do you know it is or it isn't? So from this, we can just look at the error plot, which I have deleted, but now it's back. And since it has the spikes here, it means that Runge phenomena is present. So we can say that is present. Yes, Runge phenomena is present. And of course, during the midterm, should this question show up, you need to explain it further. And for part H, if you had to interpolate this function using either an even number of nodes or an odd number of nodes, which would you choose and why? Alright, so they give us a hint. Think about even and odd function. So let's go ahead and plot the cardinal sine function again. So I'm just gonna do this and then let's run the function. Okay, this section. So here we can see that this is a even function, obviously, because both sides are symmetrical. And because of this, we would want an odd number of points, because as we can see from part C, the degree is always n minus 1. So if we take an odd number of points, the degree is always even. And therefore, we want, is it h now? H. So we want an odd number of points. And I think that concludes problem 2. I'm just double checking. Yep, so that concludes problem 2. I hope you understood what is going on, and I'll see you in problem 3. Thanks for listening.